maximum bending moment due to UDL is WL square by 8, where W is the rate of UDL, that is 4314 Newton per meter run, that we have already found out because we have taken per 1 meter length. So maximum bending moment is given by an equation WS square by 8, where W is nothing but the total weight of the pipe for 1 meter run, that is 4314 Newton per meter. Length which is given to us, that is our water main, is resting between the two supports, that is of 10 meter. So L is the 10 meter and 8 is the 8. We found out M is equal to 53925 Newton into meter. If I will multiply by with the 1000, then 53925 multiply by 1000 Newton into meter, Newton into millimeter. Now to find out the stress, I have to use the basic bending equation, that is M over I is equal to F max divided by Y max, where Y max is equal to DO by 2. Please refer the figure over here on this particular tabletop. This is our neutral axis. Then this is YT, this is YB, and as is the symmetry, YB is equal to YT is equal to DO by 2, and that is our Y maximum. So if we come over here, Y maximum is equal to DO by 2, that is 540 by 2, that is 270 mm, and if we are replacing the value, M is equal to F max is equal to M over I into Y max. M 53925 into 1000 divide by I, we have found out 1.105 into 10 raised to 9 into 270. We find out the stress, maximum stress acting is 13.18 megapascal Newton per mm square. So see the type of problem which has going to ask. What we did in this problem first, because everything is known. So if I will revise this particular problem on this particular tabletop, a simply supported beam, length of 10 meter which is given to us. If we take a section, the given section which is of hollow and internal, the water is running full in this direction along the length of 10 meter. The section which is given to us, that is dimension, that is DO and DI, we have already been found out. As thickness is given to us, we can find out the DO also. Question is going to ask, find out F max. We know that is M over I is equal to F over Y. I have to find out the F. Y is known to us, DO by 2. I we can find out as the cross section is known to us. How to find out M? As the given beam is a simply supported beam. Now the water is running throughout the length of the beam, means indirectly it has been stated that the UDL which has been given to us, but not in the direct form. So what we did, we first find out the W by adding the two weights. The first is the weight of this cast iron per meter. The next is the weight of this water which is running in throughout the length of the beam. That summation is the total weight. And then we kept over here, we use the formula WL square by 8 M I. If I is known, we can find out the value of F. I wish that you have understood this problem very well. With this, we are going ahead with the next problem. Now, let us we go to the next problem of the types for the unsymmetrical sections. In case of the symmetrical sections, the neutral axis passing through the geometrical center of the section. But in the case of the unsymmetrical sections like L, T, unsymmetrical I sections, where The neutral axis does not pass through the geometrical center of the section. Hence, the value of y for the topmost layer or the bottommost layer of the section from the neutral axis will not be the same. What happens up till now in the problems, that as neutral axis passes to the geometrical center, YYB and the YT is remain same, but in case of the unsymmetrical sections this doesn't remain same. Hence, the value of y for the topmost layer and the bottommost layer of the section for the neutral axis will not be the same, and hence we have to find the first, the neutral axis. That is, for finding the bending stress in the beam, the bigger value of y we have to use, and to find out the value of y we have to use the basic concept of the CG, and we have to find out the value of y first, then we have to find out the value of I, and then we have to find out the value of bending stress. Let us go ahead and let us solve this particular problem. A cast iron bracket, word is used, bracket. Bracket means which is connected at one end, that is fixed at the one end over here. This is known as the bracket. Other end is free. In short, it is a cantilever type of beam, that is known as the bracket of I section. I will cut a beam, it is look like as an I section. Hence, if I will visualize from one side, that is elevation, is look like this. The dimensions of the I section is shown in the figure. See the figure clearly. 200 mm top flange dimensions of 200 by 50. Bottom flange dimensions is of 130 by 50. 200 and 130 are not same. Given section is of unsymmetrical section with respect to x axis. If the maximum bending moment on the section is of 40 mega Newton into millimeter, determine the maximum bending stress. Also find out what is the nature of the bending stress. Interesting question. Find out the nature in the sense, the question which has been asked, whether that maximum bending stress which is of compressive nature or tensile nature, that we have to find out in this particular problem. Let us solve this problem right now. An unsymmetrical I section is given to us. Also, the beam type is of cantilever is given to us. M 40 into 10 raised to 6 Newton into millimeter is given to us. Hence, to find out the bending stress, we have to first find out the location of the neutral axis, and based on that we have to find out the section modulus. So now let us find the CG of the section, and let y is the distance of the CG from the bottom face, and hence y bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. Let us be understood this concept by drawing a figure over here. So if I will plot on this tabletop, this is the unsymmetrical I section is given to us with the size of 200, top flange 200 by 50 mm, bottom flange is 130 by 50 mm. 50 mm is the thickness of the wave, and the thickness length is of 200 mm. So what I did, I have divided into three parts. 1, 2 and 3. I have divided the whole I section into 3 parts. First part, second part, and third part. So if I am interested to find out y bar, what is the y bar? I have defined it, and first of all an arbitrary neutral axis, and I will say this is my y bottom, that is y bar, and this has been found out by the formula a1 y1 plus a2 y2 plus a3 y3. Look it out. What is a1, what is a2, what is a3, what is y1, what is y2 into y3. Please over here on this particular PPT. So a1 is the area of bottom flange, 130 cross 50, that is 6500 mm square, where y1 is the distance of the CG of area a1 from the bottom face, that is 50 by 2, that is 25 mm. If you want to refer the figure, please come on to this particular tabletop. Area, this one, that is 130 into 50. Now this is my reference line. I have used reference line. CG is over here, then this is my y1, and that is 50 by 2, that is of 25 mm on this PPT. A2, area of the wave, that is of 200 by 50, 10,000 mm square, and y2 is the distance of the CG of A2 from the bottom face, that is of 50 plus 200 by 2, that is of 50 plus 100, that is 150. Please come on to this tabletop if you want to refer the figure over here. The area for web is this one, 200 into the 50 thickness. Now the CG is over here, and this distance is of 200 by 2, and this is 50. So this distance is 200 by 2 plus 50, that is 150, that is of y2. Come to this particular PPT. A3, area of the top flange, that is 200 by 50, that is of 10,000 millimeters square. Y3, that is the distance of the CG of A3 from the bottom face, that is of 50 from the bottom, plus 200, that is the web portion, plus 50 by 2, we achieve 275 mm. Please refer these things on this particular tabletop. Area, third one, this one 200 by 50, rectangle portion. Now this is the CG, then this is my y3. What is that? First 50 plus 200 plus it is center, so this distance is 50 by 2, that is of 275. So if we come this, that is we found out a1, y1, a2, y2, a3, y3. If we are replacing over here, so y bar is equal to 6500 multiplied by y1 25 plus 10,000 multiplied by 150 plus 10,000 multiplied by 275, that is y3, divide by a1 plus a2 plus a3, and simplifying this simple equation with the calculator, we found out y bar is 166.51 mm. Hence the neutral axis is at a distance of 166.51 mm from the bottom face. Now just refer the figure. So from this bottom face I obtain the y bar, because this is a neutral axis. I obtain this neutral axis available from this bottom face is 166.51. The overall depth is 200 plus 50, 250 plus 50, 300, 300 minus 166.51. I obtain the YT, distance from the neutral axis to the top fiber is 133.49 mm. So Now we find out the moment of inertia of the section about neutral axis. I is equal to I1 plus I2 plus I3. I1 is the moment of inertia of the bottom flange about neutral axis. That is equal to moment of inertia of the bottom flange about an axis passing through its CG plus AH square A1 plus distance of its CG from the neutral axis. Let us be understood this concept over here on this particular tabletop. We have a figure like this. This is my y bar. Now this is the neutral axis or CG passing for the first area. So I1 is equal to 1 by 12. This is a 130. This is 50. 130 into 50 cube. That is, this is the moment of inertia for itself, its CG, plus AH square, area 130 into 50 into h square. H is the distance from this CG to the neutral axis, that is of y bar minus 50 by 2 square. And if we see these things on this PPT, that is of 6500 multiplied by 16651 minus 50 by 2, that is 25 square, and we simplify it. We found out the value as 131517,186.6 millimeter raised to 4. Similarly, you can find out the value of I2 and I3 right now by yourself. And we found out as it is given over here, and summation all the three things, we achieve I as 284907234.9 millimeter raised to 4. Now once I is known to us, we can find out the value of F max by a simple equation, m over I is equal to F max over Y max. Y max is nothing but the maximum between Yt and Yb,